All right. We're going to go through note cards 28, 29 today with a little bit of 27. These are on the natural exponential function as well as the logarithmic ln of x function and exponential and log functions in general. As we talked about in class already, e to the x is a very special function. It's an exponential function that grows and grows and grows. Its derivative is the function itself. So to get an idea of what that means, if you consider right here on the graph of e to the x, right at 1, we know that point is the point 1 comma e to the first power, so that's 1 comma e. So that's the height of the function right here. It turns out also, if you plot the you plot the tangent line at that point, it's going to have a slope that is exactly equal to the value of the function. In other words, e to the x is a very special function in that it is its own derivative. Incorporating the chain rule into that, the derivative of e to the u is e to the u times the derivative of u. So we'll go through a couple of sample problems here. So using this formula right up here, the derivative of e to the 2x minus 1 is going to be e to the 2x minus 1 times the derivative of 2x minus 1, which is 2, in simplest form, 2e to the 2x minus 1. So pretty straightforward. In 2, we've got a quotient, so we're going to have to use the quotient rule. By the quotient rule, we're going to have low d high. The derivative of e to the 2x is e to the 2x times 2. Minus high d low all over low squared. Let's see, we can simplify that a little bit. This is 4e to the 2x minus 2e to the 2x all over 2x quantity squared. And then if we go one step further, we can divide everything by 2. 2e to the 2x minus e to the 2x all over 2x squared. That's my simplest answer right there. Which of the following is equal to f prime of e? Well, we know by the limit definition of the derivative that d dx of e to the x, the derivative of e to the x, is the limit as h approaches 0 of f of x plus h minus f of x all over h. And if I want f prime of e, then I'm going to plug e's in to all the x's. So f prime of e is therefore going to be the limit as h approaches 0 of e to the e plus h minus e to the e all over h. That is going to be C. So there you go. All right, then the last one here, let f be a function given by f of x equals 3e to the 2x, and let g be a function given by g of x is 6x cubed. At what values of x do the graphs of f and g have parallel tangent lines? Parallel tangent lines are going to occur when the derivatives are equal to each other. So let's figure out what makes these derivatives equal to each other. Let's start by finding the derivatives. Derivative of f is 3e to the 2x times 2. The derivative of g, 18x squared. So what I'm looking for is what makes 6e to the 2x equal to 18x squared. This is calculator allowed, so I'm going to go ahead and graph this. I've actually already graphed it ahead of time right over here. Let's bring this in from Desmos right over here. And you can see that what I did here is I graphed in green, that is the parabola 18x squared, and in blue it is the exponential function 6e to the 2x, and I've identified the intersection point on Desmos as occurring at, oops, that's highlighter, as occurring at x is equal to negative 0.391. So we did most of that in class already. Just want to make sure you had it all. Now, what we didn't quite get to in class are our logarithmic derivatives. So let's go jump to the natural log function. The natural log function, it's now note card 29, that is the inverse of the exponential function e to the x. So if I go onto my graph here and I draw in the line y equals x, about like that, our exponential function, you would see, would go something like this. We saw that on the previous. This is the inverse of it. This is the natural log. A couple things about the natural log. As x goes to infinity, this function grows infinite, although very slowly. And as you head towards 0, it tends down to negative infinity. That's what you see on number 3 right there. And a couple of facts about the natural log you should remember. The natural log of 1 is equal to 0, as seen right there. And e and ln cancel each other out. E to the ln of x is equal to x, in the same way that ln of e to the x would be equal to x, because natural logs and exponential functions cancel each other out. So the derivative of the natural log function is actually quite simple. It's simply ln of x derivative is equal to 1 over x, or incorporating the chain rule, the ln of u is 1 over u times the derivative of u with respect to x. Let me just show you where that comes from. It's pretty easy to do using implicit differentiation. If I let y equal the natural log of x, I can raise both sides of that equation to the power of e, and I get e to the y is equal to x. Now let's take the derivative with respect to x on both sides of this equation. The derivative of e to the y with respect to x is e to the y times the derivative of y with respect to x. The derivative of x is 1. Now I'm going to solve for dy dx by dividing both sides by e to the y. When I do that, cross out those e to the y's. The result is dy dx is 1 over e to the y. But as we've already established up top here, e to the y is in fact equal to x. Therefore, the derivative is 1 over x. So what we've established there is the fact that you see right over here that the derivative of the natural log of x is 1 over x. Incorporating the chain rule, the derivative of the natural log of u, 1 over u, times the derivative of u. So let's apply those rules and do some sample problems here. So here's the natural log of t squared plus 3. I'm going to apply this rule over here. V prime will be 1 over the inside times the derivative of the inside. In simplest form, 2t over t squared plus 3. All right, number 2, I have a product. I will use a product rule. Y prime is first, derivative second. So the derivative of the ln of 5x to the fourth is 1 over 5x to the fourth times the derivative of 5x to the fourth, 20x cubed. And then I have to add to that second derivative first. So let's see, in simplest form here, we're going to have an x to the fourth divided by an x to the fourth. Those are going to cancel out, and then 20 divided by 5 is 4, so this is going to be 16 plus 4 natural log 5x to the fourth, and there's my answer for my derivative. Number 3, I have what looks like a quotient, but in reality it can be written as 1 over 3 pi ln tangent of x. Just isolate this out here. So this is just a constant multiple. So when you find the derivative, that constant multiple will just stay as a constant multiple, 1 over 3 pi. Derivative of natural log is 1 over the inside multiplied by the derivative of the inside. Derivative of tangent is secant squared. So I'll just go ahead and leave my answer just like that. So that was the chain rule along with the natural log derivative rule. Number 4, we've got a function. We want the slope at x equals pi over 4. So I'm going to start by taking the derivative, dy dx. Derivative of 2ln is 2 times 1 over the inside, multiplied by the derivative of the inside. Derivative of secant of x is secant x tangent x. I can go ahead and cancel out a secant here. Result is 2 tangent of x. Now I want the derivative at pi over 4. So y prime at pi over 4 is 2 tangent pi over 4. Tangent of pi over 4 is 1. Final answer, 2. Number 5, we're going to write the equation of the tangent line. So I need to start by taking the derivative. F prime is derivative of negative 2, 0. Ln of x squared, derivative 1 over the inside, multiplied by the derivative of the inside. We can simplify that down to 2 over x. 2 over x. And then plug in 1. F prime of 1 is 2. That's the slope of the tangent line. Then to get the y value, I need to evaluate the function at 1. Negative 2 plus ln of 1, that just equals negative 2 since ln of 1 is 0. So now I can write the equation of my tangent line. Y minus the y coordinate, y minus negative 2, is equal to the slope, 2, times x minus the x coordinate, x minus 1. And there's the equation of my tangent line. And then finally, number 6, we've got a function. We want to find f prime of 0. So this is ln of a bunch of stuff. So when I take the derivative, the outermost function is the log. So the derivative of that, as we know, is 1 over the inside. So that's x plus 4 plus e to the negative 3x. Then I have to multiply by the derivative of the inside. The derivative of the inside is 1 plus 0 plus e to the negative 3x times negative 3. E to the negative 3x is its own derivative multiplied by the chain rule inside derivative negative 3. F prime 0, just plug 0 in for all the x's. 1 over 0 plus 4 plus e to the 0 times 1 plus 0 plus e to the 0 times negative 3. E to the 0 is 1, so this is 1/5. 1/5. 1 plus e to the 0 is 1, negative 3. That's a negative 2. Altogether, negative 2/5. So that is the derivative of the natural log function. We've got that. We also have the derivative of the exponential function e to the x. That's all these problems. Now the last thing we need to do is talk about the derivatives of exponential and log functions other than base e. So that's where I'm going to jump back to what we did on our inverse trig derivatives and come back here to these last two rules. And I'm going to put a box around these. Let's see. We'll go with orange. Right there. So compare this to our basic derivative of e to the x. Let me do it in chain rule form. E to the u, derivative of e to the u, du dx. Now, if you change your base to anything other than e, 2, 3, 4, then it's the same thing except you have an extra ln of the base a. So as an example of that, if I come down here, let's look at number 4 here. If this were the equation y equals e to the 3x, then the derivative would be e to the 3x times 3. But that's not e to the 3x, it's 2 to the 3x. So if I've got 2 to the 3x, what's different is when I take my derivative, I'm still going to get the function back itself, 2 to the 3x, I'm still going to have to multiply by the derivative of the inside, 3, but I have to multiply by an extra term if it's not e, and going back up here, that extra term is the ln of the base. So in this case, that would be ln of 2. That's going to be my answer to number 4. And now let's also take a look at number 6. Exponential function. dy dx is the function itself multiplied by the derivative of the inside, finally multiplied by the ln of the base. That would be my answer to number 6. So it works just like the e to the x. You just get the extra ln of the base. And in fact, if you applied that same rule up here, ln of e is just 1, and we just make it go away. Works the same way. Now, let's go back up here again. Recall that the derivative of the natural log of u is 1 over u du dx. Well, this is the same thing with an extra 1 over the ln of the base. So an extra 1 over the ln of the base. So same derivative, but log, remember that ln of x is actually log base e of x. So this is base e. When your base is something other than e, you have to also divide by the extra ln a. Sometimes it's easy to remember this by writing it as, instead of this form, writing it as 1 over u ln a du dx, and then this spells ulna, 1 over ulna. This is sometimes an easy way to remember it. All right, so let's take a look at a couple examples that involve that. Here, I've got log base 10. So dy dx is going to be equal to 1 over the inside, that's my u, times the ln of the base, that's my ulna, multiplied by the derivative of the inside, which is negative sine of x. So I could write this as negative sine x over cosine x times the natural log of 10. So that's my answer to that. And then for number 7, I think what I would do first is I would rewrite it as log base 6 of x to the negative 1/2. That's 1 over x. That's my u. So when I take my derivative now, dy dx, I'm going to have 1 over u multiplied by the ln of the base multiplied by the derivative of the u, or the derivative of the inside. So let's see, we can do some manipulating here. That x to the negative 1/2 can move on up to the top. That's x to the 1/2. Still have my ln 6 in the denominator. I've got a negative 1/2, and then x to the negative 3/2 can move down into the denominator and become x to the 3/2 in that way. And then I can actually cancel out this x to the 1/2, take away on 1/2 here, and the result will be x. 3/2 is 1.5. I'm taking away 1/2, so that would be just x to the first power. So let's see, simplest form then would be negative 1 over 2x natural log 6, and that is my answer. All right, so that is your note cards 28 and 29. That's derivatives of e to the x and ln of x, and then coming back to 27, because for some reason I have them on here, those are the derivatives of your general exponential and logarithm functions. And that's it. I hope you have a nice day. Goodbye.